Every day, we breathe in a silent killer. Air pollution, fueled by growing cities and traffic, is a global health crisis. It's linked to cancer, asthma, and respiratory diseases, with millions of deaths worldwide. We know traffic is a major cause, especially during the day. But for a city planner or even a resident, a crucial question remains: how bad is it? Right here, right now, and what will it be like tomorrow? Today, to make smart decisions, we need more than just general warning. We need local data and predictive power. That's why we built a complete full stack system to monitor and predict air pollution in real time. Our solution is broken down into three phases: hardware, data pipeline, and machine learning.
First, the hardware. We designed a robust, low-cost IoT device. It's built around an ESP8266 controller and a bank of high-sensitivity sensors to measure the most critical pollutants. This includes sensor for PM2.5 particles, carbon monoxide, ozone and nitrous oxide, ammonia and CO2, as well as temperature and humidity. To maintain all these analog sensors with the ESP8266, we integrated a 16-channel demultiplexer. Second, the data pipeline. We deployed the hardware in Vanwadi, a densely populated area in Pune with industries nearby. For 30 days, 24/7, the device monitored the environment. Every 20 minutes, it processed the sensor values and pushed a data pack over the Wi-Fi to a cloud database. We used Google Apps Script as a WebSocket broker to log all 11 parameters directly into a Google Sheet. Third, the machine learning. With our dataset of 578 unique data points, we set out to build a predictive model. We pre-processed the data and split it, 80% for training and 20% for testing. We tested a range of algorithms: linear regression, lasso, ridge, decision tree, and random forest.
The results were outstanding, while standard linear regression performed the worst. Our random forest and lasso regression models were incredibly accurate.
This flowchart details the entire journey of our data from the physical device to the cloud database. The process starts when the hardware collects a new set of sensor readings. It then posts this data package to our custom Google Apps script, which first checks for a valid connection. Once verified, the script acts as a traffic controller, splitting the complex data packet according to each specific gas and pollutant using a switch case. It then communicates with the Google Sheet to request the last row used, increments this value to find the next available slot, and reverts with the target row number. With this information, the device requests to insert each value into its specific column in the new row. The script writes the data and sends a done bit back to the device. The hardware checks for a successful status code, and if it receives a 200 OK confirmation, it knows the data is safely stored and enters a 20-minute wait period before the entire circle begins. This created a seamless automated pipeline that fed our database around the clock.
In this project, the ESP acts as the main controller, reading all sensors and uploading the data over Wi-Fi. For air quality measurement, we are using MQ135 for CO2 and ammonia, MQ07 for carbon monoxide, and MQ131 for ozone and other gases. For dust level, we have added a PM2.5 optical sensor that detects fine particles including infrared scattering. The GST22 handles temperature and humidity, so we can correlate gas readings with changing environment conditions. Since the ESP only has one analog pin, a 16-channel demultiplexer lets us switch between multiple analog sensors clearly. Altogether, this hardware setup gives us a compact system that monitors gases, particles, and weather parameters in real time.
So this is the code that we are using, and now I'll just upload the sketch to the ESP8266. After the upload is complete, we'll turn on the serial monitor, and here we can see that the ESP is calibrating. After the calibration is complete, the system will start taking measurements every 10 seconds and will update the Google Sheets immediately.
This project is more than just an experiment. It's a blueprint for a micro-level warning system. Local governments can use this data for smart urban planning, like creating road diversions during peak pollution to protect public health. By combining custom IoT hardware with powerful machine learning, we can finally predict pollution and start building a healthier, safer future.